tool.
Okay, can you see my screen?
Yes, totally.
How do I?
Great.
Let me. Okay, perfect. Nice. Yeah. So first of all, thanks again, Matthias, for inviting me. My name is Alexander, and I'm a PhD student at the University of Sherbrooke here in near close to Montreal in Canada, and I also work for Terra Quantum as an applied scientist. And I'll talk about tensor networks today. So that's a big subfield in in quantum computational science, if you will. And recently we had a nice reviewing the applications of tensor networks for quantum computing. So I'll talk a bit about this. But first, a bit about me. My background is in physics and experimental and theoretical physics. I come from Moscow, Russia, and I did my bachelor and master's there up until 2019, and then I moved to Canada to work for 1Qubit, a quantum software startup in Vancouver, where I was working mostly on machine learning for tomography, which is the other, sort of the other subfield of quantum computing, if you will. Then in 2020 I started my PhD in Sherbrooke, and then at some point I stumbled upon the guys from Terra Quantum, and we've been working together since 2022 on closely related problems to what the paper was about. So yeah, just a bit to motivate my talk today. It's going to be, first of all, it's not going to be a technical talk, more of a review talk. Also, I don't, since the things, like there are many things to cover, this is going to be like a limited review in the sense that I'll give you some very interesting and nice papers to read. So probably, I hope you'll have a bit of like a broad picture of what's the state of this field of sciences right now in, and yeah, hopefully it'll spark some interest. Yeah. Anyway, so first of all, we've been seeing, like you probably all saw, we've been seeing a lot of interesting things happening in quantum computing recently, including the fault tolerance, like the road to fault tolerance from Google and Quantinuum. Then we've been seeing actually the first one of my collaborators for the review. They published a very nice article where they used the certified random numbers that they're generated using the Continuum machine, and that's all also the machines operating in the regime below error threshold, and this is like one of the I think one of the maybe even the first actually useful things generated by quantum computer. Anyway, and then finally, people forget about this a bit, but I think it's an important part as well. So we've been also seeing a bit of progress in the algorithms. So when we think about quantum computing, people usually think, oh, there is Grover, there is Shor, there is maybe some people know about these algorithms for solving linear equations, which also provide some speed up. But for example, like last month, there's been this paper and Seth Lloyd is one of the most renowned quantum computing researchers out there. So they published an algorithm which exponentially faster finds the matrix determinant. So I think, like the progress is slow, but we're somehow getting there. So I feel like we're still good to get some fruits out of this field. And then there's also the second part, which is quantum-inspired algorithms, which is somehow close but different in the sense that these are algorithms which take inspiration from, which come from quantum physics often, and but at the same time they don't rely on any quantum hardware. So this is purely classical, and apparently there's also been many things happening there. So for example, I stumbled upon these several nice reviews. Of course, they're all big, but just skimming them and seeing what people do will give you a nice overview of this area. And tensor networks here, in my opinion, is the best of both worlds. So it's the intersection of the two in a sense. First of all, as this toolbox comes from quantum information, quantum physics, so it's inherently suited for quantum hardware. So in the sense that your tensor networks naturally describe states, processes, circuits, and so on and so forth. But at the same time, these computational tools don't require quantum hardware, so you don't need these things. You can some small models you can play on your laptop, and then there's also been a lot of open source code effort recently and papers and everything. So these are, in my opinion, this is a computational tool which sort of is at the intersection of the two. And it's been interesting when we were writing, when we were deciding how to motivate the review we're writing. I did this small plot by scraping the archive. So the archive has the API you can scrap to track the number of papers, and to get metadata and everything. And we did this plot with the cumulative number of papers per year, and we found out that first of all, like you can see, there's been lots of papers per year coming recently, and this is an absolutely dramatic volume, but and it's still going up. But we found that apparently by now almost all tensor networks papers mention quantum. So you see that and quantum computing can seems like a drive for the research in tensor networks, and vice versa. Yeah, sorry. Just to close the motivation part. So here we decided to do this just because you see the intersection of two fields is growing bigger. And with this, yeah, let's move into just these just the basics of these methods. So first of all, it's a tensor network is basically a mathematical expression. So it's the formalism in which you write tensors as bubbles with legs, and then open legs usually mean the open indices, and then by the indices you don't sum over, and then if your legs connect, it's called a contraction. So for example, it's here. Okay, I don't see my mouse, but yeah, you see on the left of the slide the contraction. You can represent different decompositions. I didn't draw, so there's many things you can do. I didn't have space to draw them all here. But one of the most important parts are one of the most important things is the decomposition of tensors. I specifically wanted to stress on the decompositions here, just because it's honestly one of the cornerstones at which all the methods involving tensor networks reside. Sorry, and for example, here I draw the SVD, and then if you look at algorithms for finding ground states or everything for storing quantum states, all of them use SVD, the singular variable decomposition. I think you're all aware what that is. But the cool thing is that I like to mention that it's based on the Eckart-Young theorem, which guarantees you the best approximation of a given rank, which allows you to do approximate, to keep the bond dimensions and to keep things approximate during contraction. And why you want to do that is that if you just store everything, if you don't truncate your tensor network, the volume of your space grows exponentially, so the number of tensors and number of tensor elements in the tensor grows exponentially. So apparently you don't want to do that, just because if you scale the system, then you won't have enough RAM. For example, I think the numbers for the qubits are, so like the best methods for sparse matrices allow you to store like 30 qubit, so like 2 to the 30 qubit state. And with, for example, with this kind of approximation, which is called the matrix product state, you can go like thousands of qubits, and of course you are limited in the rank, you're limited in the entanglement you can store in these states, but this is already like two orders higher than your dense or sparse methods.
Alex, if we interrupt you.
Yeah, sure, go ahead.
Cool. I mean, we tend to be a bit like less structured and formal in the sense that interrupting. So, I was wondering, I have a question. You mentioned that the Eckart-Young theorem like is optimal when you approximate. But this is when like the singular values are like most of them are 0, right?
So the thing is, no, the theorem works for all for general matrices, and but then I think what you mean is that the error of approximation depends, of course, on how many singular values you throw out. So the more, of course, the more you trim, the more error you have. But you know that the great result in a sense is that the amount of norm you lose is the sum of the singular sum of the squared modulus squared of the singular values. So if they are small, then you know the sum is small, and then you don't lose much. But if we call it in physics, we call it the spectrum, and then you know if we say if the spectrum is flat, meaning that all these singular values are the same, then you know you don't want to throw out too many. But then if your spectrum is peaked near the first k singular values, then you're good to go, because you know the norm goes down, and so you can throw them away. This okay. And so yeah, and the beast I showed you before here, which is here in the near the letter A, is called matrix product state in physics, or it also emerged in computer science, and people call it tensor train. Yeah, so this is like one of the first tensor network algorithms. I think it's the first tensor network algorithm invented in the 90s, and then it was used to find, it's actually crazy. So it was used to find ground states of gapped Hamiltonians. You don't need to know what this means, just what you need to know is for finding, for modeling quantum states of matter, like one-dimensional chains, spin chains, etc. And now people use this for example, like later I'll cite one of the papers where it's used for natural language simulation, like the simulation of generating like an RNN, basically, like a recurrent neural network. So it's crazy the universality of these methods, if you will. But what I want to say here is that then physicists came up with a whole bunch of these different tensor networks. For example, the one in B is used for two-dimensional systems, and then the one in E is used for systems with special structure of entanglement in them. So there's a whole zoo of these methods, and I will not even talk about the old optimization methods for these networks, or for even for approximate contraction methods. But generally there are, if you need to to tweak the tensor elements, there are like some physics-based methods. Then there's also like a simple machine learning method, if you will. It's the gradient methods. There are some geometric methods but at the same time, this is usually also optimization, but for example, optimization on the manifold of unitary matrices. And you can also do Monte Carlo sampling with these models. So this is just to sum up, this is a bunch of very, very powerful computational methods coming from physics from the 90s. The things we wrote our review about is how these methods are used in quantum computing right now. Because we've been seeing lots of, so I've been working in around quantum computing since 2017, 2018, and then since that time, I had time to see how many different sub problems around the quantum computer, in a sense, can be tackled with these problems. So so first of all, it's to name the things where tensor networks are used. First of all, there comes simulation, and I think this is maybe the most important role where people use tensor networks for simulating quantum circuits, and this is naturally your quantum circuit is a tensor network. So there's also been a bunch of methods how to simulate all these quantum advantage experiments, and it's interesting. It often is the case that the simulations are usually more energy efficient, or come up with more fidelity and everything. So there's been several cases. I don't know if you followed, but there's been several cases where people were announcing, oh, like, look, we achieved quantum. Let's see, I think it's called quantum utility these days. They're changing names all the time, and it's been people were like, okay, we have a quantum advantage experiment here. You cannot do this with any classical algorithm. You cannot compute what we computed. Then a week later, there's some group coming up and saying, oh, look, we invented our own tensor network algorithm which does that, on several days on a supercomputer, and then your claim debunked. So there's this. Then there is also quantum circuit generation. What this means is that sometimes you need to, for example, prepare a state for your quantum algorithm, and theoretically what the state should be, but you don't know, like, for the experimentalists in the room, they need to know what operations to apply to their state to make the state that they want. So these methods allow you to basically decompose a state into a sequence of operations which people need to apply in the lab actually to prepare that. So this is, in a sense, one can think about it as uploading data into a quantum computer, like preparing the input state. Then there's also quantum state tomography, which is the inverse of this operation, which is extracting the state from a quantum computer, which is, of course, one of the cornerstone problems is in quantum computing. So then comes the error correction part, where people use tensor networks for decoding quantum error correcting codes, and this is actually the topic I'm working for my PhD. And there's also the general decoding problem is Sharpie hard, so there are a bunch of algorithms for that, and all these algorithms, like some codes are very hard to decode, and here tensor networks allow you to balance between accuracy and efficiency, because you can control the bond dimensions, the contraction rate, and everything. And finally, there's quantum machine learning. So I will talk a bit more, since the focus of your group is the machine learning part. I'll talk a bit more about this, but I had just to tell you, I'm not like a big expert in this field, so I'll just share my what I found when I was writing this. Just share my findings with you. Hopefully this will help. And so in quantum machine learning as well, so as I witnessed, there's also been many papers and many applications on like trainability, or on compressing, or on studying how if the gradients vanish, if you have these barren plateau issues, and so on and so forth. So yeah, I'll talk a bit about the machine learning part now. So first of all, what I found out is that apparently there were two reviews. The first one is more of a review. The second one is less of more of a technical paper. But apparently there's been already many results at the intersection of the two subfields of quantum information, quantum computing, if you will. And one of the things was, of course, this memory efficiency, this compressing part. And this is not it's not surprising that these models that were suited for compressing the quantum state can now do this, can do this in QML, in a sense. And then the second thing was the correspondence of tensor networks to circuits. So this is this graph on the right is taken from the first paper, from this review, and the idea is that your different models, different tensor network models that come from quantum information, that come from quantum computing, if you in a sense, they map directly to quantum circuits, and so this allows you to basically have one-to-one correspondence between the two, and then from what I understood, that this helps you do better training, and since many of the tensor networks correspond to shallow, meaning like small quantum circuits, then this allows you to model them efficiently with your classical resources. And I think this leads you to a third point of intersection here. It's the trainability. So just because these tensor networks often, because of their structure, they don't have barren plateaus, then this allows you to train efficiently on the classical computer. And again, so the key takeaways here, from what I found, is that like you have the compression part, and since you have the compression part, you have better training part, and then the thing I like about tensor networks is that there is a natural correspondence between the classical realm and the quantum, and there is also, so if the different models correspond to different circuits, which allows you to boost your imagination and do the things in both worlds, in a sense. There's one thing I didn't have a lot of time to read about, although I'm still curious about it. I want you to know as well, is the application of tensor networks in classical machine learning. And apparently, so first of all, there's this website. I think it's curated by people from the Flatiron Institute in New York, and so there they keep track of all machine learning applications of tensor networks. I don't know to which extent it is up to date, but it is it has a lot of volume. There's lots of papers there, and I think many of them are very interesting. Also there is one, it's a review-ish paper, I would say, by the advisor of my master's thesis, Jacob Biamonti, who is actually now in Montreal here at the École Technologie Supérieure. So they wrote a paper about tensor networks in machine learning, and then there is, from what I found, there are three main areas of application. First of all, is more of the algorithm part. It's applications to supervised learning and unsupervised learning, and the third one is model compression. And for the supervised learning, there's been, for example, there's also many papers if you search about this, but one of the first one was by Miles Studenmar, who's in the Flatiron Institute I mentioned before. Right now, so there they reproduced basically some classification results on MNIST, and I know that for machine learning people, MNIST is like a toy problem, but they were physicists at that time. I think they were super happy that they took matrix product state from condensed matter physics, and then they were able to classify digits with it. And then also people did the similar things in the unsupervised learning realm. So for example, the one I mentioned is people did RNN type like modeling of language, or there was a paper also from Miles where they compute the data features learning, like unsupervised learning paradigm, the learn features of data. And the last but not the least is actually people in Terra Quantum did some model compression with tensor networks, which I think is super cool, because they were able, so they reported almost 15% of less memory with losing just 3.2% of accuracy. And since I'm not since I'm not a big machine learning person, I think these numbers are, for me at least, they're quite impressive. And so yeah, I think this is mostly it. Just to wrap up, I hope you did grasp a bit of what's happening in, in our field, and how the two fields cohabitate together. Thanks for listening, and yeah, if people have any more questions or wanna see wanna for me to share the slides, there is my email here at the bottom, or you can text me in the chat or somewhere. So yeah, thanks for listening. I'll be happy to answer your questions.
Super, thank you. Super nice review of what's going on. I don't know if people have any question. I encourage.
I do have a question. First, can you hear me first?
Yeah, I hear you.
Okay, cool. First of all, thank you for your talk. It was really interesting. And I'm wondering a bit about the decompression aspect of tensor networks. Like, as far as I understand, to compress a machine learning model or whatever with tensor network and achieve this amazing compression ratio, you still need the original model to be trained, right? So you're not skipping that part, because to compress that, you need to know the correlations that are in the weight matrix and so on. So you still have to train, right?
Yeah, that's a very good question. I think you're right. I don't know. So first of all, I don't know exactly if there exist methods, if you can somehow overpass this issue. For me, at least from what I understand, I don't think it is possible. Like I think you still need to train the full thing. But it's actually back in the days, it was one of the I think like 2017, 2018, there was a big rise of these neural network quantum states. I don't know if to which extent some people were following, but like this is like first when people applied restricted RBMs, they were able to store a quantum state in an RBM, and then this whole thing came out. Like people were coming up with all these transformer quantum states and everything, and I think with LLMs it also was escalated to to the extreme. But the thing is that you still needed to get the training data for these neural network quantum states. You still need for example, an MPS, and you need to train it, and you need to get the samples, or you need the samples from an experiment. And then you need to know that this experiment is certified and everything's good. So yeah, I see what you mean, and I don't know to which extent this is a big problem or not.
Okay, thank you.
Can you tell us a bit about the training part with tensor networks? And I mean, there are some scenarios in which you talked about training, no?
Yeah. So
how they get the gradients and this stuff? Do you have the automatic differentiation mechanism inside?
Yeah, you do have. So so you do have the autograd features, and for example, there's this tensor network package called QIMB, which is I think it's one of the best, if not maybe the best package out there. And so for example, there they have examples where they train. I think they train a quantum circuit, a classical fully classical code, where they train a quantum circuit using different types of automatic gradient, and then even more. So for example, one of my previous papers where we used tensor networks for simulation, so we use this model called I'm sorry, I don't think you see it. It's close to E, so it's the one with pink balls. It's called MIRA, the multi-scale entanglement renormalization ansatz, and we use the autograd. It's called the Riemannian gradient. So it's the gradient in the manifold of unitary matrices. So you optimize your tensor elements but your tensor always stays in isometry. So in isometry means that if I contract this tensor with a complex conjugate, it's going to be an identity. And so there are even such, optimization methods where you can optimize, you can tweak the elements, but then your tensors will keep their properties. And then this also helps you to mitigate some these barren plateau issues, helps you converge faster. At least that's what we found, so that these methods converge faster than just traditional gradient descent. So yeah, it's all equipped with these methods, if you will.
Sorry, this is super cool, but I think I want to understand it better. With this Riemannian optimization, you say like you have a manifold, and you need to move, right, in this manifold and optimize, okay? And what you say is that your optimization method guarantees that you stay in the unitary manifold somehow. Does this work for other manifolds? I never heard about, like, I read it in the review, and then I said, what?
Yeah, sure. So I think it does, even though the other ones can be. So my co-author had a Python package written for that. I think it's called QGopt. Yeah, I think it's called QGopt. And there, I think he has in his package he has examples of different manifolds. But for physicists and for the quantum info people, this Riemannian gradient is the most important, because in quantum many models have isometric tensor system, many tensor architectures have isometric tensor system, or if you have a circuit, then your unitary. So unitary is it's just an isometry, but it's just a tensor with two legs. So a generalization of a higher order tensor would be an isometry. So unitary is also an isometry. Now, so if you need to optimize your gates, then this optimization also works. So yeah, I hope this answers.
Yeah, super cool, super interesting. I don't know if people out there curious about something.
Yeah. Hey, hi. Do you hear me?
Yep.
Yeah, I'm a little bit curious, because you said that you were working also, like, I think, in error correction or things like that. But yeah.
Oh, sorry, go ahead.
Yeah, do you hear me? Yes.
Yeah.
Yeah, okay. So I was also curious about these kind of applications besides these machine learning ones. So because you say you have been working on this.
Yeah, of course. Let me just find. I had this. We had this nice table in the paper. Yeah. So mostly in the error correction part, the biggest application is. So I would say there are two main applications. First of all, there is decoding, and then there is the. In two words, what's happening is that you have a big sum. You need to sum up many parts. It's called like maximum likelihood decoding. So you need to compute a sum of exponentially many parts, right? So you cannot do this exactly, but you can, if you represent the sum as a tensor network, so then you can approximately contract it. So you can contract the tensors while keeping the bond dimension. So this gives and this converges to optimal decoding at the limit of infinite bond dimension. So this is the biggest part. But the drawback here is that these decoders are not fast enough. So they're very accurate, and you can, for example, the different error correcting codes have different error correcting capabilities, in a sense that they tolerate different amount of noise, different amount of errors. And if you want to study a code, if you came up with a quantum error correcting code or a classical error correcting code, you want to compute its properties such as a threshold, and then there you need a very accurate decoder, and then here a tensor decoder would be enough, would be good. But then in the real laboratory, in the real quantum computing experiment, you need the order of time you need to compute the corrections are, I think, nanoseconds, if I'm not mistaken. So you need to be really fast. And there, for example, what Riverlane, a UK company, what they do is that they have a decoder which sits on an FPGA, and then they put this FPGA into the same fridge with a quantum computer, so that it's very cold, it's very fast, and then you can achieve this speed. So this is the first application, and then the second one is error correcting codes, which are, it's called like tensor network inspired, but it's just that there is also one-to-one correspondence between a tensor network and the quantum error correcting code. And there, the good thing is that these types of codes, they already come with an efficient decoder, because you can construct a decoder from this tensor network. So there's everywhere you have one-to-one correspondence, and it's called also, I think it's called quantum Lego formalism, and it's more on the theoretical side. I will admit there is not many, like it is a niche research subfield, I would say, but that's what that's the main two.
Yeah, so for me, it's like when working with these tensor networks, you have a very powerful tool, but you do not really know which kind of applications are the ones that are suitable for that. So I did not know of this error correction, and I wonder, like, which kind of tensor network, like, exactly do you use so it can capture correctly, like, the entanglement of this?
Yeah. So there, what happens is that you don't use, like, when you need to decode, you don't use, for example, or this cartoon, yeah. So you don't use, for example, these things, because these are like structured models for representing quantum states. But what happens is that you have let's say, like, you have a graph. It's called like Tanner graphs in error correction, right? So you have these Tanner graphs, and then you have your like stabilizer measurements. So you need a contraction. So in the end is just a tensor network which is taken, which is mapped onto from a Tanner graph. So it's not like it's like with the quantum circuits, you can do, you can create a matrix product state, and then you can apply gates to it, or you can just write your circuit as a tensor network and then just contract it. And you will get, if you want to compute amplitudes, you will get the same result if you don't truncate anything. And apparently the state-of-the-art methods, so the methods where people simulated these random, what's it called, RCS, the random circuit sampling experiments like Google did, the tensor networks they used is not any of those, not any of these physics tensor networks, but they just represented the circuit as a network, and then they contracted. You find some sophisticated methods of contraction which keeps entanglement, and you get the results. So you see, it's not that you always use these models, established models.
Yeah, I've read about this in quantum machine learning. It can also happen with like neural networks. You can also write them as a tensor network, like with no general, like with not defined like form, a lot more either depths or MPS. Okay, so thanks.
Yeah, thanks for the question.
I have another question. Maybe it's a bit dumb, but how do you use tensor networks for quantum state tomography?
I will not answer the technical details because I don't know. I haven't used them. I know that.
Okay,
I know that. Yeah, I haven't done this myself. But from what I understand is that I guess it's a sort of an optimization algorithm as well. So you say that, okay, my state is, so what you need to do is that you'll say, okay, my state, it will be in the form of a matrix product state, for example. And then you have, you can sample measurements from your quantum device. So the problem, just naively, the problem you end up with is that, okay, I need to somehow tweak the elements of my tensor network given the measurements in the poly X or Z or whatever basis I measured in. So yeah, and then you need to come. I guess the idea here is just to come up with some clever optimization routine, but just naively, the problem it all just boils down to optimization.
Okay, thank you.
Sure.
Alex, in this nice table that you are showing to us, it took my attention, this property of analytical interpretability that is placed as an advantage for tensor networks for quantum machine learning. To what extent this analytical interpretability is? How do you see this analytical interpretability beyond, for instance, the analytical interpretability that variational quadrant algorithms could have? Or
Yeah, that's a good question. I have an answer to this, but I'm not sure it's the correct answer because we have we actually had someone from Alexei Melnikov's group who was leading the QML section, because I'm not by any means an expert in QML, but from is that you can, it's like you know, for example, maybe a good analogy would be the how's it called, the convolutional neural networks, where you have these filters, and then once you learn the filters, you can see that the filters often correspond to some, you know, you can see that, for example, when it's reading a face of a human, it's reading like the edges of the face. That's my understanding of how these things work. And so there, since you have predefined tensors on some places, so maybe you can somewhat think of it in this regard. So you know, if you have, for example, if you have a mirror tensor network like this hierarchical thing here on the right. I'm sorry, again, it's covered by the cameras, and I don't see my mouse, so I cannot move it. Then you know, you have this translates into gates, and then these gates, like one of the gates sit between the two qubits, you know, covering the two qubits. Then maybe you can say that, okay, like I take information from these two. So it's all this. I don't think there is really any like big explanation here. So at least that's my understanding. But yeah, thanks for the question.
What I was wondering is, you mentioned at some point the barren plateaus, which is like a big topic in quantum machine learning, variational algorithms in particular. Here in barren plateaus, you randomly change the parameters of your quantum circuit, and you see like which is the structure of this manifold, right? And in particular with the gradients. I was wondering what happens now. You talked about optimizing tensor networks, okay? How much is it known about like random tensor networks and the structures that emerge? Like, do people, I mean, we talk about unitary designs in when it comes to, I don't know, barren plateaus or or optimizing quantum circuits. Is there any sort of analogy with tensor networks? I guess so.
That's a good question. I think regarding the barren plateaus, I don't know. I don't know too much about this. I know that, so actually, also recently there's been a very nice review. I'm still postponing to read it, but I wanna at some point get to reading it. It's called I think it's called Barren Plateaus in Variational Quantum Computing. It was recently.
It's from Marco.
I'm sorry, it's from your group?
No, it's not our group. It's the Los Alamos group.
Yeah, it's the Los Alamos group. Yeah. So that's a very nice review, and I think so. There they talk about they mostly cover the things you mentioned. As for me, so I know, for example, that there were these analytical results, which I think are very nice. Is that your like these hierarchical tensor networks, like, you know, the ones having like this hierarchical structure like Mira, or maybe the Tritian as well, they don't experience these barren plateaus. So as soon as you have like you know, like a cone which expands, then I guess this and they prove somehow it, then there is no vanishing of the gradient.
Yeah, there are many results. Like, we are a bit more in the jargon of quantum machine learning and whatever,
Yeah.
because we take care of that. And there are like, so if you take Mira or Mera, I don't know how people say it, Mira, right?
Yeah.
Then this is very similar, as you were saying, of the quantum convolutional neural network structure. And there is like an all by now result in which like these ansatz do not showcase barren plateau. And it's trainable. And then like the story goes on as it follows. Like people have strong evidence that if there are no barren plateaus, then it's classical. You can simulate this classically, the training procedure.
Oh yeah, I think I know the result you're talking about. Yeah, I think I saw this at some point. Yeah.
So so I was wondering a bit, like when you were saying by the end of your talk, that you can actually simulate like shallow quantum circuits efficiently using tensor networks, if this cannot be seen actually from this point of view, in which, well, actually yes, because it's classically simulable.
Yeah, I totally agree. There is lots of like there's lots of controversy here in the sense that sorry, can you? I think I'm hearing myself in.
Oh, sorry.
Yeah, sorry about this. Yeah, I was just about to say that there is this. There's been lots of. I saw this result you're talking about, and I think it's also that there's like this logical loop, right? When you have like you want to have a model that's easy to train. You know, if you talk about the quantum models, but then once it's easy to train, it's classically simulable, so you don't really need the quantum computer. Yeah, I don't know. There's also, from what I understand, there's also like this. The notion of efficiency is a bit vague in a sense that you can have a polynomial scaling of like training or something, but then if this polynomial is very high degree, then for example, for smaller systems, you can still have worse training than an exponential one, but with some like small factor. So there is also, and I don't know to which, as I didn't really code these things up myself, or I didn't really use them in the machine learning, I mean in the quantum machine learning in my research, then I cannot really tell you practically to which extent these things are important or not. But I see what you mean, and yeah, I think it's a very like there is in QML, I think that might be an obstacle.
Yeah, I mean, in any case, it's like nobody has the answer. So, but I was wondering, like you mentioned the PEPs, which is the pair entangled projective states, and then you were like showing some quantum circuit structures. I'm not very sure, like if this is correct, like if there is an analogy between the PEPs and the hardware efficient ansatz. In which you have like two body correlations and you stack it together to build the quantum circuit.
I think I think it's more, yeah, I see what you're talking about. I think this hardware efficient ansatz, I think it's still like a 1D, it still can be considered as a 1D model. So I think it's more like it's still like if you would model that, you would still have an MPS, you would still have like a 1D chain. But as for so usually to have a tensor network model, to have it correspond to a circuit, you need to have it's a bit technical, but you need to have it's called a canonical form. So for a tensor network, a canonical form is that if for example for an MPS you would have all the tensors but one being isometries. And they can be isometries from the right if you contract them with themselves on the right or on the left. So then the MPS, it's called like a left canonical or right canonical. And for a tensor network to correspond to a circuit, you would need to have isometries, because you would need to map these isometries to unitaries in the circuit. But for the PEPs, there is no known canonical form. So this model is it's computationally very hard. It's not often used just because it doesn't have the canonical form, and then when you have a canonical form, many things get simpler, like the observables, the computing of observables, the contractions, and everything. And since the PEPS doesn't have the canonical form, I don't know if it can even correspond to a circuit.
I see. Okay. And then, so my question was a bit more into this bond dimension, which seems to be like some sort of a course of dimensionality or whatever.
Yeah.
So I understand, like, if the bond dimension grows, then tensor networks are not an efficient tool anymore for classical simulation of these systems. So my question was like, okay, but if you can actually never mind if it's the hardware efficient answer, it's an MPS or a PEPS. If you can actually span the whole unitary group by stacking together many two-body correlators or two-body gates, okay, in your quantum circuit, then in principle, like, no, so my question is like, how does the bond dimension looks like this if your circuit grows enough? I understand, like, you span the whole dimension and then you're fucked up, no? Or
yeah, if you, so practically what happens is that you set a limit on one dimension, and then in all of your contractions you respect this limit so you don't go over. But of course, if you do all the contractions exactly, if you just multiply things all together, of course you will have the growth, the bond dimension growth, and then usually things escalate pretty quickly in these models. And so yeah, because usually when you, for example, when you like contract a unitary or contract like just simply if you take a matrix product state and apply MPOs, so this would correspond to this like 1D chain over here, and then you would apply a similar chain of operators. Usually it will, the bond dimension will grow exponentially. So you are, it's, yeah, you need to limit that.